Good morning, my dear students. Welcome to the chemistry class. In my previous class, I completed the discussion of D block elements. Today we will start from A block elements. Okay. If you look at the modern periodic table, then just below the 7th period, two additional rows are there. Okay. These elements are called A block elements because the last electron enters into the F orbital. These elements are also known as transition elements because they are placed in between transition elements but in a separate place and having the same properties of transition elements. Okay, like showing color, and they have the property like complex formation. Okay, like this. Now these F block elements have filled or partially filled, partially filled F orbitals in n-2 energy cells. That is the anti-penultimate cell. Okay, third to the valence cell. Okay, valence cell. The next cell is called penultimate cell, and then inside next cell is called, that is third cell. Okay, from the outside it is called anti-penultimate cell. These elements, okay, block elements are divided into two series. One is called 4F series, another is 5F. 4F series is called lanthanoids, this is 4F, and actinoids is a 5F series, okay, or actinides. In lanthanides, 4F subcell is successively filled, and in actinides, 5F subcell is successively filled. Okay, that is why they are called 4F and 5F series. Today, I will discuss only the lanthanide series. This series has 15 elements. First is there lanthanum. Then there is cerium C, lanthanum is La. Next prosiodinium is PR. Okay. Then is neodymium, that will be ND. Promethium is there, PM. Samarium is there, or samarium, it is its symbol is SM. Europium, its symbol is EU. Gadolinium is GD. Terbium is TB. Disoprosium DY. Holmium HO. Then erbium ER. Then is thulium TM. Then is yttrium YB. And the last element of this lanthanide series is lutetium, or sometimes it's called lutetium, and its symbol will be Lu. Symbols will be Lu. Okay. Next, these elements are called lanthanides because these elements follow lanthanum. After lanthanum, that cerium to lutetium is there. Okay, and they have similar properties like lanthanums. That is why they are called lanthanides. Next, we will discuss the general properties of lanthanide. First, we will discuss the electronic configuration. If you look at the electronic configuration, their general electronic configuration will be xenon 54. Then the F orbital will come. So F orbital will be 4F 1 to 14 because F orbital can take maximum 14 electrons. Then it will be 5d1 6s2 like this. Okay, and the first element, that is the lanthanum. Lanthanum will be what? What is the electronic configuration of lanthanum? Xenon 54, 4f0, 5d1, lanthanum is 57. Okay, this is 54. 4f0, 5d1, 6s2. This is the electronic configuration of lanthanum. After lanthanum, there is cerium. Cerium will be 58 and its electronic configuration will be xenon 54. Okay, then 4f2. Okay, 4f2, 5d0, 6s2. Okay, it will be the electronic configuration of cerium. Next, if you write that after cerium there is promethium, here it will be 4F3. Okay, and the last element in this way you will practice this thing. Electronic configurations are in your syllabus. Okay, you have to practice the electronic configuration, and finally the last element is lutetium or lutetium. Okay, lutetium. Okay, lutetium, the atomic number will be 71. And its electronic configuration will be xenon 54, 4F14, 5D1, 6S2. This is the electronic configuration of lutetium. Okay. Next, we will discuss the physical state. Lanthanides, okay, are silver white metals, and samarium or samarium is still hard, okay, and its melting point is very high. Next, density, these lanthanoids have high densities around 6 to 9 gram per centimeter cube. Okay, you know that mercury has the highest density, is very high. Okay. Next, melting point and boiling point. So these elements, that means lanthanides and actinides, okay, they have fairly high melting point, around 1000 Kelvin to 1200, okay, Kelvin. Only samarium melts at very high temperature. Temperature will be around 1623 Kelvin. Okay. Next, we will discuss the ionization enthalpy. The ionization enthalpies are very low. The fast ionization enthalpy of these lanthanides are very low, around 600 kilojoule per mole. But second is high, quite high. So these lanthanides are highly electropositive in nature because of this low IP values. Next, we will go for the oxidation state. These lanthanides show +3 oxidation state in general. Some elements also can display +2, +4 states, but they are less stable. Okay, that means +2, +4 are less stable compared to the +3 oxidation state. Lanthanum and gadolinium and lutetium exhibit only +3 oxidation state. Okay, that depends on the electronic configuration. We know that half pill and full pill are very much stable. Okay, from that you have to give the reason. Europium and ytterbium, okay, so they will exhibit +2 oxidation state. Next one is cerium is there, and then after cerium there is Tb is there, okay, terbium. They will exhibit +4 oxidation state, okay, +4 oxidation state. Next, we will discuss the oxidation states of the others like samarium and terbium. They will exhibit +2 oxidation state. Next, there is promethium. Promethium and neodymium, they will exhibit generally +4 oxidation state. So that depends upon the electronic configuration, that you have to practice. Next, we will go for the radius, okay, or radii of this transition ions or inner transition elements. Okay, they are actually forming that tripositive ion. Okay, and the size of the this tripositive ions, okay, decreases as we go from lanthanum to lutetium. Lanthanum has longest radius 1.06 angstrom and lutetium has the smallest radius 0.85 angstrom, and this decrease in the ionic radii from 1.06 angstroms to 0.86 angstrom in steps, okay, averaging about 0.015 angstrom is known as lanthanide conduction. And what is the cause of the lanthanide conduction? This is because of the low shielding or screening effect of the 4f electrons, 4f orbital. Okay, as we move from left to right, in lanthanide series, the number of 4f electrons increases by 1 unit, but the pore shielding of the f orbitals increases the effective nuclear charge. Okay, so electrons are decreasing, number of protons are increasing, but effective nuclear charge will be very high. Okay, and because of the pore shielding effect of the f orbital electrons. Okay, and causing a regular decrease of radius, and that is known as lanthanide contraction. Because of this lanthanide contraction, consequences, what will be the consequence of the lanthanide contraction? There will be regular decrease in their honey radii. There is regular increase in the electronegativity. Okay, there is regular decrease in their tendency to act as a reducing agent. Sometimes because of these things, some properties will be almost same. Okay, and you also see the, because of this lanthanide contraction, okay, and the effect will also see in the 2D 3D series also. Okay, 2D and 3D series. Okay, next we will discuss the color, like transition elements. Okay, D block elements, they are, because they show colors and they are complex, their ions are colored because of D transitions. Here also few M3 plus ions of lanthanides will show color, okay, in their solid state as well as in their solution. The color is due to the FF transition of electron. Okay, so lower level F, there will be splitting of F orbital in presence of ligand, and lower F level or lower level F orbitals, okay, electrons will absorb visible light, and it will go to the higher level, then it will come back and radiate some amount of energy, and that is why they will show color. Few are showing. I can tell that tellurium 3 plus, it will show green color, and diisopromium 3 plus, it will show yellow color. Okay. Next, lanthanum 3 plus and lutetium 3 plus do not show any color change. This is due to absence of the partially filled F orbital. Okay. Next, we will discuss the complex formation. Lanthanoids form complex compounds, okay, mainly with chelating ligands, okay, such as EDTA, oxalic acid, ethylene diamine, etc. We have multidentate donors, okay. But these elements have poor tendency to form complexes due to their large size, okay, although they have +3 oxidation state, okay. Next, we will discuss the chemical reactivity. These lanthanoids are quite reactive, and they resembles like calcium. Their property will be similar like calcium, and this lanthanum will react with nitrogen, forming lanthanum nitride, and they will react with acid, this lanthanum, that will form hydrogen gas. And if you take sulfur dust and lanthanum, if you apply heat, then you will get lanthanum sulfide. If you add some water, then you will get lanthanum hydroxide plus hydrogen. Okay, and because of this lanthanide contractions, they will show basic property. Okay, so finally we will discuss the use of these lanthanoids. Okay, in niche metal, okay, that you are using in lighters, okay, for producing spark, there it contains 40%, around 40% cerium. Cerium also used in the glass, okay, reducing spectacles. Cerium magnesium alloy are also used in the flashlight powders, okay, and cerium salts are used in dyeing clothes, okay, as well as some cerium metals and their compounds are using as a catalyst, okay. Cerium oxide and thorium oxide are used in the lamp maintenance, okay. So in this way, today we have completed the discussion of the lanthanoids, and next day we will discuss about actinoids. So thank you for watching the video.